A solid cylinder of radius r and thermal conductivity K1 is surrounded by a cylindrical shell of inner radius r and outer radius 2r and the thermal conductivity K2. The equivalent thermal conductivity is, options are K1 plus 3K2 by 4, 3K1 plus K2 by 4, 4K1 plus K2 by 3 and K1 plus 4K2 by 3. It is given that we have a cylinder like this, above which there is a cylindrical shell. It is like this. The radius of this one is r, the radius of this one is 2r, that is this shell has inner radius of r and outer radius of 2r. Thermal conductivity of this one is K1, thermal conductivity of this one is K2. As you can see in the figure, this cylinder is parallel to this cylinder. Therefore, I have to use the formula for parallel combination of resistances, that is given by 1 by r effective is equal to 1 by r1 plus 1 by r2, r is 1 by k into L by A. Therefore, this formula reduces to k effective into A effective divided by L is equal to 1 by r is K1 A1 divided by L plus 1 by r2 is K2 A2 divided by L. L get cancelled and left with K effective into A effective is the total area, because that is the area that is exposed to this, to this side. The total radius is 2r, therefore, I get pi r square, pi into radius square, that is pi into 4r square, 2r whole square is equal to K1 into A1 is area of the inner cylinder, that is pi r square, plus K2 into area of the outer shell. The total area is 4 pi r square, the inner area is pi r square. Therefore, area of this shell is 4 pi r square minus pi r square, which is 3 pi r square. Pi r square get cancelled and left with 4 into k effective is equal to K1 plus 3K2. Therefore, k effective is equal to 4 into k effective is equal to K1 plus 3K2. Therefore, k effective should be K1 plus 3K2 divided by 4. K1 plus 3K2 divided by 4. As you can see there, option A is the right answer. Suppose we have a solid like this, the area of cross section of the solid is A, thermal conductivity of the solid is K and the length of the solid is K. Then suppose the temperature at one of the ends is T1, the temperature at the other end be T2, let T1 be greater than T2, that is this part is at a higher temperature and that part is at lower temperature. Now, due to this temperature difference, heat flows from left to right now. The amount of heat flowing per unit time is called rate of heat flow. Heat is measured in joules, time is in seconds, therefore, SI unit of this one would be joule per second. Amount of heat flowing per unit time depends on the thermal conductivity of the solid, the area of the cross section of the solid, the temperature difference between the ends of the solid and the length of the solid. The exact dependence is here. Rate of heat flow is given by K into A into T1 minus T2 divided by L. As you can see from this formula, if the thermal conductivity is more heat flows. If the area of cross section is more heat flows. If the length is less, more heat flows, and for a higher temperature difference, heat flowing would be greater. Now, there is another point we will note here. Suppose I have an area of cross section here like this. Suppose the heat coming to this into this area of cross section be Q and the amount of heat going out of the cross section be also be Q. That is amount of heat going into the cross section is exactly equal to amount of heat leaving the area of cross section. Such a state is called steady state. In the steady state, any heat that is coming into an area of cross section in the conductor is exactly equal to amount of heat going out of the cross section in the conductor. Here is the problem. Two cylindrical conductors of same area of cross section have lengths L1 and L2 respectively. They are in contact in series and the free ends are maintained at temperatures T1 and T2 respectively. The temperature of the junction in the steady state is K1 T1 L2 plus K2 T2 L1 divided by K1 L2 plus K2 L1, K1 T1 L1 plus K2 T2 L2 divided by K1 L2 plus K2 L1, K1 T1 L1 plus K2 T2 L2 divided by K1 L1 plus K2 L2, K2 T1 L1 plus K1 T2 L2 divided by K1 L2 plus K2 L1. These are the options. The problem states that we have a conductor like this. Let us call this conductor A. This is connected to another conductor B of same area of cross section, but the lengths are different. The length of this one is L1, the length of this one is L2. The areas are same. The area of this one is A, the area of this one is A again. The temperature of this one is T1, the temperature of this one is T2. The thermal conductivity of this one is K1, thermal conductivity of this one is K2. We have to find the temperature of this one. Let us call the temperature of junction be T. Our problem is to find the temperature of the junction. In the problem, it is stated that it has reached a steady state. That means heat coming into this junction is exactly equal to heat leaving the junction. Let us for now suppose that T1 is greater than T2, therefore heat flows from left to right. In the steady state, heat entering the junction is exactly equal to heat leaving the junction. We know the formula for rate of heat flow, which is given by K into A into T1 minus T2 divided by L. K is thermal conductivity, A is area, T1 minus T2 is the temperature difference, L is the area. In the steady state, Q by T for both of these must be same. Therefore, K1 into A1 into T1 minus T, that is the temperature difference, divided by its length is L1 is equal to, for that one the rate of heat flow is K2 into area is A2 into temperature difference is, this is higher temperature, that is lower temperature because heat is flowing from left to right, T minus T2 divided by L2. But the areas of cross section are same, therefore A's get cancelled. I can cross multiply these and I can simplify. I can simplify for T, I can just separate T's and I can put the other on the other side, and simplifying this one I get T, the junction temperature T is equal to K1 T1 L2 plus K2 T2 L1 divided by K1 L2 plus K2 L1. This is the junction temperature. The answer turns out to be A. The correct option is A. Now, let us discuss specific heat capacity and principle of calorimetry. For a given heat, all the substances do not heat up at the same instant. The difference in temperature for different substances is different for a given amount of heat. That is due to this property called specific heat capacity. Specific capacity of a substance is the amount of heat energy required to raise the temperature of 1 kg of a substance by 1 Kelvin. S is equal to heat supplied divided by mass into change in temperature. The SI unit is joule per kg per Kelvin. You can see here we are not changing the state of the substance, but only changing the temperature of the substance. Whenever we are not changing the state of the substance, but only changing the temperature of the substance, we consider specific heat capacity. But there is another kind of heat capacity, that is called latent heat, which is defined by amount of heat energy required to change 1 kg of a substance in one state into another state without changing its temperature. It is the amount of heat energy divided by mass, SI unit of joule per kg. In the case of latent heat, we do not change the temperature, but only change the state. In the case of specific heat capacity, we do not change the state, but only change the temperature. Now, I will come to principle of calorimetry. When we keep a hot object and a cold object in thermal contact, the hot object loses heat, whereas the cold object gains heat. Principle of calorimetry states that heat lost by hot object is exactly equal to heat gained by the cold object. In calculating these heat lost and heat gained, these formulae when written in these forms may be very useful. Heat is equal to delta Q is equal to ms delta T, mass into specific heat into change in temperature, or delta Q is equal to mass into latent heat. Whenever there is difference in temperatures, then I use the formula delta Q is equal to ms delta T. Whenever there is change in state, I have to use delta Q is equal to ms latent, m into latent heat. These formulae may be used here. Another point to be noted here is that whenever we calculate heat lost, whenever this temperature difference comes, I have to do T initial minus T final. In the case of heat loss, T initial minus T final. In the case of heat gained, I have to use T final minus T initial. Now, we will solve a problem on principle of calorimetry using these ideas. Here is the problem. The temperatures of equal masses of 3 liquids A, B and C are 12 degrees centigrade, 90 degrees Celsius and 27 degrees Celsius respectively. When A and B are mixed, the temperature is 16 degrees Celsius and the temperature of mixture of B and C is 23 degrees Celsius. The temperature of mixture of A and C is 18.2 degrees Celsius, 22 degrees Celsius, 20.5 degrees Celsius and 16.75 degrees Celsius are the options. Now, I have 3 liquids, one is A, the other is B, the other is C. A is at 12 degrees Celsius, B is at 19 degrees Celsius and C is at 27 degrees Celsius. If I mix A and B, the temperature is 16 degrees Celsius. If I mix B and C, the temperature is 23 degrees Celsius. What is the temperature if I mix A and C? At the temperature of the mixture of A and C be capital T. My job is to find T now. What is the value of the temperature of the mixture of A and C? That is to be calculated. Now, when I mix A and B, A gains heat whereas B loses it. By principle of calorimetry, heat lost by B is equal to heat gained by A. As there is temperature differences, I have to use ms delta T, mass into specific heat into change in temperature here. Heat gained by A is equal to heat lost by B, that is the formula I will use. That implies mass of A into specific heat of A into change in temperature of A. That initial temperature of A is 12, the final temperature is 16, therefore change in temperature is 4 is equal to mass of B into specific heat of B into change in temperature of B is it's 19 here, 16 here, the change in temperature is 3. It is given that the masses are equal, therefore masses get cancelled. That gives me SB is equal to 4 by 3 SA. That is one fact I will use later on. Next, let us see what happens with the mixture of B and C. When I mix B and C, B gains heat whereas C loses it. Heat gained by B is equal to heat lost by C. I will use again the mass into specific heat into change in temperature formula. heat gained by B is equal to mass of B into specific heat of B into change in temperature of B. Change in temperature of B is, it's 19 now, 23 later, therefore change in temperature is 4 is equal to mass of C is C, mc, into specific heat of C is Sc, into change in temperature of C is 23 to 27, I mean 27 to 23, that's 4, 4 gets cancelled, mc and mb get cancelled because the masses are equal, that gives me Sb is equal to Sc. Now, what happens when I mix A and C? Now, A is at a lower temperature, C is at a higher temperature, therefore, A gains heat, C loses it. Heat gained by A is equal to heat lost by C, which implies mass of A into specific heat of A into change in temperature of A. What is the change in temperature of A? Final temperature is T, final initial temperature is 12, therefore, T minus 12 is equal to heat lost by C, Qc is equal to mass of C into specific heat of C into change in temperature of C is, that is heat lost, therefore, initial temperature minus final temperature, that is 27 minus C. Masses get cancelled and left with Sa into T minus 12 is equal to Sc. Sc is equal to Sb, but Sb is equal to 4 by 3 Sa into 27 minus T, 27 minus T. I can cancel these S's, I can cross multiply this one here, that gives me 3T minus 36, 4 is here, 27 into 4 is 108 minus 40, that gives us 7T is equal to 144, which implies T is equal to 144 divided by 7, which is equal to 20.5 degrees Celsius. It's a temperature of the mixture of A and C is 20.5 degrees Celsius. The option is C, 20.5 degrees Celsius. Now, let us discuss some important thermodynamic processes. The first process is isothermal process. Isothermal process is a process in which the temperature does not change. The temperature of the system remains constant, therefore, delta T, that is change in temperature, is 0. Therefore, change in internal energy for an isothermal process is also 0. An isothermal process obeys the relation pressure into volume equals constant. For an isothermal process, always pressure into volume is a constant. Next comes adiabatic process. In an adiabatic process, the system is thermally isolated from the surrounding. You cannot supply heat to the system, you cannot remove heat from the system. That is, heat supplied or heat removed is 0. An adiabatic process obeys the relation PV power gamma equals constant, pressure into volume power gamma. Gamma is called a ratio of specific heats, we will discuss it later. PV power gamma equals constant. The next one is isobaric process. Isobaric process is a process which happens at constant pressure, that is, change in pressure should be 0. For an isobaric process, delta P equals 0. And for an isochoric process, the change in volume is 0, that is, the process happens at constant volume. For this process, isochoric process, the work done would be 0, because work done is equal to change in pressure into change in volume. As the change in volume for an isochoric process is 0, work done for an isochoric process is always 0. Now, I have shown some of the PV diagrams for these thermodynamic processes. As you can see here, this represents isothermal process, this represents adiabatic process. This is a hyperbola, this represents adiabatic process. Isothermal process and adiabatic process are almost look the same, but adiabatic process has a larger slope, whereas isochoric process is exactly vertical, the slope is infinity. For an isobaric process, the slope is 0. Among isothermal and adiabatic process has more negative slope, whereas isothermal process has a smaller slope. Now, let us solve some problems on these concepts. here is the problem. The PV diagram for a gas expanding from state 1 to state 2 is as shown in the figure. During the process, the gas is option A heated continuously, B cooled continuously, C heated in the beginning and cooled towards the end, D cooled in the beginning and heated towards the end. Here is the graph, it is a PV diagram. As you can see here, the pressure is decreasing and the volume is increasing, that is correct, the gas is expanding. Now, to find out whether it is heated or cooled, we cannot see from PV diagram because heating and cooling is not shown here. Now, let me draw two isotherms for the given gas. This is one of the isotherm for the given gas, that is another isotherm for the same given gas. There are the two isotherms. Isotherms are the graphs which show PV equals constant. But as I can see here, if I draw a vertical line here, for the given volume, this pressure is lower than this pressure. That is, upper curve has a higher pressure than the pressure for the lower one. Therefore, if this represents T1 temperature, this represents T2 temperature. By Charles' law, as pressure is directly proportional to temperature, T1 should be greater than T2, because this isotherm is at a higher pressure, this isotherm is a lower pressure for the same gas. T1 is greater than T2, this represents higher temperature. Now, I denote this point by A, this point by B and this point by C. The given graph you can see here starts at A, goes to B and goes to C. It is first touches isotherm A, this isotherm, then it touches this isotherm, then it touches this isotherm. That is, at point A the temperature is T2, at point B the temperature is T1 and at point T the temperature is T2, and as you can see here T1 is greater than T2. Therefore, temperature of B is greater than temperature of A and temperature of B is greater than temperature of C. That is, this temperature is lower, this temperature is higher, this temperature is again lower. What is the conclusion? This is at lower temperature reaches a higher temperature, therefore, from A to B it is heated. Coming from B to C the temperature decreases, therefore, it is cooled. That is, the gas is heated in the beginning and cooled towards the end. Therefore, the correct option is C, heated in the beginning and cooled towards the end. Now, we shall see ideal gas equation. Ideal gas equation is given by PV equals mu RT, where P is the pressure, V is the volume, mu is the number of moles in the system you are considering, R is called gas constant, T is absolute temperature. This applies for ideal gases. Now, there is a problem with the finding mu, the number of moles. Number of moles is given by the given mass, the mass you are given with, divided by molecular mass, m divided by m. For example, if you take helium, if they give 8 grams of helium, then given mass is 8 divided by molecular mass of helium is 4. Therefore, number of moles in 8 grams of helium is 2. That is how we find number of moles. But you should be very careful with about this T. T is absolute temperature. It should not be substituted in either degree Celsius or degree Fahrenheit, but it should always be substituted in terms of kelvins. Pressure into volume is equal to mu RT is called ideal gas equation. We shall solve a problem of this concept now.